In this video, we're going to continue to look at L'Hopital's rule. In this video, we're going to look at functions which have the indeterminate form 0 times infinity, or 0 times negative infinity, or negative infinity times 0, that sort of thing. And we'll notice that L'Hopital's rule does not apply to functions in that form. So what we're going to do is we're going to apply some algebra tricks, or possibly some trigonometry properties and rules, and we're going to convert it, the original function, to something that does have the form 0 over 0 or infinity over infinity, where we can apply L'Hopital's rule to the new fractional form. So here's an example that I'd like you to try to do. Let's see if you can do this one. Take the limit as x approaches 0 from the right side of sine of x times ln of x. Notice that sine of 0 is 0, and then ln of x approaches negative infinity from the right side, so this has the form 0 times negative infinity. See if you can rewrite that sine of x over or times ln of x as a fraction, so that you either have 0 over 0 or infinity over infinity. See if you can apply L'Hopital's rule and make it work out. It turns out there's sort of two ways to write it. One way has the form 0 over 0, the other one has infinity over infinity. And one of those is a little bit easier to work with in terms of what you get out of L'Hopital's rule. So if it looks to be really messy one direction, try it the other way. All right, you try it now. Press pause. Okay, so it turns out, I think, in this case, that if we'll rewrite this as ln of x over 1 over sine x, 1 over sine x is cosecant of x. So rewrite the sine x as 1 over cosecant of x, and then rewrite it as a fraction like this. Now, both the numerator and the denominator are going to either infinity or negative infinity. Okay, so that is the form that L'Hopital's rule applies, or one of the two forms. So we can apply L'Hopital's rule to just take the derivative of the top and the bottom, and then take the limit. The derivative of log of x is 1 over x. The derivative of cosecant of x is minus cosecant of x, cotangent of x. We're taking the limit as x approaches 0 from the right. Now I'm going to rewrite this. I'm going to put the x down to the denominator. Okay, but when in doubt, rewrite everything in sines and cosines. So that's what I'm going to do here. Let's see. Cosecant is 1 over sine, so that puts a sine of x in the numerator. We have the minus and the x in the denominator. Cotangent of x is, let's see, cotangent is cosine over sine, but this is a reciprocal of cotangent, so that's sine over cosine. So it gives us another sine, so we have sine square of x in the numerator, and it leaves a cosine of x in the denominator. Now let's see what happens as we let x go to 0. Well, let's see, sine of 0 is 0, square root is 0, so the numerator is going to 0, and separately cosine of 0 is 1, but then we have this x is 0 going to 0 here. That gives us the form 0 over 0. Okay, we can apply L'Hopital's rule again. So take the derivative of the top and the bottom. This is u squared, so that's 2u times derivative of u, so that's 2 sine of x. Derivative of sine x is cosine x, that's 2 sine x cosine x. And the bottom, we're going to need to apply the product rule. So that's the first, negative x, times derivative of the second. Derivative of cosine x is negative sine x. The two negatives make that term positive. And then we have the second term, cosine of x, times the derivative of the first. Derivative of minus x is just negative 1. Now, I believe this is actually continuous at x equals 0. Look what happens if we just plug in 0 everywhere. Let's see, sine of 0 is 0, times 2 is, well, sine of 0 is 0. Cosine of 0 is 1. 2 times 0 times 1 is 0. And the denominator, sine of 0 is 0, times 0 is certainly 0. And then minus cosine of 0, but cosine of 0 is 1. So we end up with 0 over negative 1, which in fact is 0. So if we were to graph this, we would expect to see then a hole in the graph at 0, 0, which is actually since this is not defined on the right side of 0, so this is only defined, I mean, it's not defined on the left side, it's only defined on the right side of 0. That's going to be a boundary point that's actually an open dot boundary point. And so we see this oscillation here that's increasing oscillation, okay, growing, the top of it's growing like a kind of like a logarithm curve there. and we see the endpoint here right at the origin, which is an open dot endpoint. So it starts with an open dot endpoint and then bounces up and down bigger and bigger as it goes out to the right. Okay, time to try one more. So I think we're just going to do these two in this video. Compute the limit as x goes to infinity of x times tangent of 1 over x. Okay, so as x goes to infinity, 1 over x goes to 0. Tangent of 0 is 0. But x goes to infinity. So this has the form, again, infinity times 0. See if you can do something like this. Something like what you did on the last one. See if you can do that. Do it with this one here. See if you can work it out yourself. Press pause now. Now there might be more than one way to go at this, but here's the way I did it. We did x times tangent of 1 over x. I wrote that as tangent of 1 over x over 1 over x. Actually, to tell you the truth, I first tried it as x over cotangent of 1 over x, and when I did the derivatives, things didn't cancel out as much as I'd like. So I went back and tried it this way, and things worked a little bit better for me. So sometimes it's a little trial and error. See if something will work out better for you, and if it doesn't, try something else. So here, the derivative of tangent of u, okay, is secant. What? No, that's not right. It's secant square. Okay. Let's see if we can fix that. Derivative of tangent is secant square of x, secant square of u, and the derivative of the u is minus 1 over x squared. So that's remember, u is x to the negative 1. The derivative, that's negative x to the negative 2, which is minus 1 over x squared. And of course, that's exactly what we have in the denominator. Those two things cancel out, and what we should have now is the limit as x goes to infinity of secant square of 1 over x, and I think actually this limit whole thing is wrong. Oh yeah, and the graph bears that out. I didn't look closely enough at the graph. Okay, so this is actually, then we can essentially pull this limit all the way in here. Okay, and the limit as x goes to infinity of 1 over x is 0. And so this becomes this part here just becomes 0. Secant of 0, 1 is 1, and 1 squared is 1, and so the limit is 1. Okay, and so we should see a horizontal asymptote of y equals 1 on the far right, and it turns out it's also the same on the far left. And so if we graph this, this is what we get. We get a horizontal asymptote of y equals 1 right there on the far right and the far left, and the graph does bear that out. Now, actually this graph is not graphed correctly in here close to 0. Some wacky stuff happens right here. What happens here is between, say, negative 1 and 1, 1 over x takes over on all possible real values between negative 1 and 1, except for 0. And so what happens here is the tangent then takes on basically all kinds of numbers in between there. And so this thing is jumping up and down, crazy in here with lots of ups and downs and vertical asymptotes all over the place. And so it actually doesn't have a limit as x goes to 0. And that's not really apparent in this graph. But of course, we weren't concerned about that part of the graph. Really, the only part we were concerned about is this part way out here to the far right. And if you look, you can see that it turns out to be the same thing as you go out to the far left as well. Okay, in the next video, we'll look at another class of examples where it has the indeterminate form infinity minus infinity. And again, we cannot apply L'Hopital's rule, but like the form 0 times infinity, we can manipulate it oftentimes to get a form 0 over 0 or infinity over infinity where we can apply L'Hopital's rule.